So the directions said use logarithmic differentiation to do this. Sometimes it makes it easier. So what I want to do is, and usually when I have to do logarithmic differentiation, I always use ln, not log base something else, because that way, because if you've looked at those videos already, you know that if y equals log base some other base of some value, the derivative of that is 1 over u times the natural log of the base times du dx. And if it's ln, the natural log of e is 1, so that's why using e is the way to go with that. It saves a step. Sometimes we can't. Sometimes it's in a base, and we need to do that. So, but this one we don't. There's no log in it, so we're going to introduce a log to break it up a little bit, to make it a little easier to take the derivative of. So I'm going to take the ln of y, and then you remember the square root is the same as raising something to the 1/2 power. So here I'll show that. So I'm going to do ln of x plus 12 to the 1/2 power, and then because that's a power and we're taking a log, we can use that power rule for logarithms and just bring the 1/2 down in front. And because I'm multiplying because I'm multiplying these two expressions, I can break those out to the sum of two logs. And then, oh yeah, here I'll do that. So 1/2 times ln x plus ln of x plus 12. And then, honestly, what I'll do is I'll distribute that 1/2 through, just so I don't lose it, and sometimes it makes it easier to have done that. So notice I haven't done any calculus yet. I'm doing algebra. So ln y equals 1/2 ln x plus 1/2 times ln of x plus 12. Now let's do some calculus. We'll take the derivative. The derivative of ln something is 1 over the something times the derivative of the something equals, and that's just a constant, so 1/2 times the natural log of x is 1 over x, plus 1/2 times the derivative of x, which is 1, so we don't have to really worry about that. And that's times 1 over x plus 12, and the derivative of that linear function is 1, so we don't have to worry about that. So here, let me do some moving up. So then what's going to happen is we've got a couple things going on. We can say this is dy dx equals 1 over 2x plus 1 over 2 times x plus 12 times y, right? But of course, we know y was that original function here. I moved it right off the screen already. Can I come back up and find it? See, y is that original function. Right here. So we're going to just replace this y with that original function. Which is the square root of x times x plus 13. So then x plus 12, not x plus 13. Or is it 13? No, it's 12. I see that. My first try was 13. Okay, now we can clean this up a little bit, and my math lab's a little funny. Sometimes they want you to clean it up, sometimes they don't. In order to add these two fractions together, I need to get common denominators, which means I've got they both have a 2, so that's okay, but that first fraction's missing the x plus 12, so I'm going to multiply this by, here, let me get it go red, x plus 12 over x plus 12, right? So that gives me x plus 12 over the common denominator of 2 times x times x plus 12. And we could multiply that out, but you're going to see here in a minute that we don't want to. And then the second fraction, I'm missing the x, so I'm going to multiply that by x over x, right? So that gives me plus x over that common denominator. And then what I see is 2x plus 12 over 2x times x plus 12. And of course, this is getting multiplied by the square root of x times x plus 12. And then I can factor a 2 out of that numerator, right? I can think of that as 2 times x plus 6. And then that 2 and that 2 can be removed. So I'm left with x plus 6 over x times x plus 12 times the square root of x times x plus 12. Now, this requires a bit of a paradigm shift if you haven't seen this enough times. Consider this problem. If I have u over u squared, right? Doesn't that just simplify to 1 over u? So if I have, let's do a simpler question before I do this next one. So if I have the square root of u over u, well, we don't have to do anything magical here. We can just think about properties of exponents. So isn't this u to the 1/2 over u to the first? And when we're dividing like bases, we can subtract the exponents, which gives me u to the negative 1/2, right? It is 1/2 minus 1. So isn't that the same as 1 over the square root of u? So what you could think of, if I have the square root of something over the thing I'm taking the square root of, I could just write that as, I could just jump right to that without doing that exponent trick. And that's what we're going to do here to get a simplified answer so that my math lab likes it. Okay, let me see. Can I delete just that? Yes, I can. Okay, so if we have this is to the first power, this is the 1/2 power, that's going to leave me x plus 6 in the numerator and the square root of x times x plus 12 in the denominator. And that is what my math lab took for an answer. Okay, so that's one that I found troublesome. Number 19 also took me 3 tries. Part of it's because I was making dumb mistakes, and part of it I was just spacing it. Dumb mistakes. So they would tell us, say, use logarithmic differentiation to break this up. So we'll do ln of y. And then, remember the fifth root we could think of as to the 1/5 power. And then because I'm going to take the logarithm of everything, I'm going to bring the 1/5 down in front. So the natural log of, so I write 1/2. Yeah, that will get it wrong, Dan. 1/5. And then, so then we're taking the natural log of t over 5t plus 1. And because I got a quotient, I'm going to have some subtraction going on, right? So 1/5 times the natural log of t minus the natural log of 5t plus 1. And then I'm just going to distribute the 1/5 through right now, so I have that taken care of. The natural log of y equals 1/5 ln t minus 1/5 ln of 5t plus 1. And now let's do some calculus. Let's take the derivative of everything. So I get 1 over y dy dt equals 1/5 times 1 over t, right? Minus 1/5 here. Minus 1/5 times 1 over 5t plus 1 times the derivative of the 5t plus 1, which is 5. So that 5 cancels off. I'm left with 1 over 5t minus 1 over 5t plus 1 times y, right? We've got to move that y over. And we know that y was equal to that cube root expression. I'm just wondering if I mixed up a problem, because the problem that I got right finally, I had cube root, and this is fifth root. I'll have to go back up and see how, but I have to delete this video. So what we're going to do is 1 over 5t minus 1 over 5t plus 1 times that original function. So I guess what my original function was the fifth root of t over 5t plus 1. And that they took as the right answer. I think. Let's see here. Let me make sure I go back up and, yeah, so that's the function I went with. So yep, so that they took, or they should have taken, because if I had done that, but I know that's not what I had before, was it? No. Actually, what I tried to do with this problem originally, I tried to combine this a little bit, and it didn't either. I made a mistake in my combination, or I didn't like it combined. They wanted it written like this. So that's my advice. Okay, with this one, I missed a chain rule my first time, so I wanted to figure, well, it's tough enough, I probably ought to show it to you. So we're going to break this up using logarithms. So the natural log of y equals, so what I'm going to do here is see how it's 3, let me get a red ink here going. It's 3 times that times that. So what I did, ln 3 plus 7 ln theta, right? Because I'm taking the logarithm so I can bring the 7 down in front, not have to worry about any power rule or anything, plus the ln of the sine of theta, all over, no, sorry, not all over. You know what I gotta do is, give me a minute here. Then what I did, notice I had to shrink things up here. Then because I'm taking a logarithm, and this is like, I'm dividing something, so I know the logarithm has a minus in front of it. So minus 1/2 times the natural log of the secant of theta. Okay, I hope that's okay with what I did. I thought of this as the secant of theta to the 1/2 power, but because I'm dividing it, I'm going to subtract the logarithm. Okay, so I think I'm okay to this point. I've got everything that I need. Now we're going to do some calculus. So 1 over y dy d theta equals now ln 3 is a constant, so that's gone. So then this is going to be 7 over theta, and since I'm taking with the derivative with respect to theta, I don't need a d theta thing, plus 1 over the sine of theta, and then what I forgot to do was do a chain rule here, so that's negative cosine theta, positive cosine theta, over 1, of course, minus 1/2 times 1 over the secant of theta, times the derivative of the secant, which is secant theta tan theta, right? I squeeze that in. See how that secant cancels off? So what have we got? We've got 1 over y dy d theta equals 7 over theta. And cosine over sine is cosine over sine is, cosine over sine is cotangent, right? Cotangent theta. And then I missed this 1/2 on one try too. So that's either 1/2 tan theta or tan theta over 2. Okay, so I'm almost there. Now I got to multiply both sides by y. So here, let me shrink this up a little bit more. So I know I've got 7 over theta plus cotangent theta minus tan theta over 2. Then I'm going to multiply that by y, and we know y is the 3 theta to the 7th sine theta all over the square root of the secant of theta. And is that what I had? Yes, and that's what they wanted. They wanted nothing else simplified. That they took that. Okay, this one, it wasn't that it was that difficult. It's just there was some algebra in there that I thought might stump some of you up, and you'd spend some time going through the help me solve it, which maybe you should, just to struggle with it a little bit to figure it out. And that way you own it. But in case you can't get it, I thought I'd record this. So we don't need to do logarithmic differentiation here because there's already a log in it. But what we can do is, because we're taking the ln of a product, we can say it's ln4 plus ln t plus the ln of e to the negative 5t. And maybe you're already seeing the algebra that I knew would stump people up, maybe. Isn't the ln of e, those are inverse operations, so what's left is just going to be the negative 5t plus ln t plus the ln of 4. So now let's take the derivative, so dy dt, or y prime. Ln of 4 is a constant, so we don't even need to worry about that. The derivative of ln t is 1 over t, and the derivative of negative 5t is negative 5. And that's the answer. You don't have to clean up any further. So this is the part that I wanted you to see, that ln of e, that's the part that throws people. Oops, what am I doing here? Now, they just say take the derivative, and they don't give you any hints. So the trick, a flag that you want to use logarithmic differentiation is when you have a variable raised to a variable. That, if you use logarithms, it'll break up the term, so you can take the derivative fairly easily. So because I'm going to take the log of both sides, that's going to allow me to bring that 6y exponent down in front of the logarithm. Same thing on the right-hand side. And now we get a couple of products we have to do, right? So, and the 6 is just a constant. So y times the derivative of ln x, which is 1 over x, plus ln x times the derivative of y, which is dy dx times the ln of x. I wrote it that way. You could write ln x dy dx if you wanted to. So I got the left-hand side done, and we'll do the same thing on the right-hand side. So 5's the constant. X times the derivative of ln y is 1 over y times dy dx. Plus the derivative of x is 1, so it's just ln y. So we've got to isolate these dy dx's, don't we? So let's distribute the 6 through. So 6y over x plus 6. Well, actually, let me do this. I'm going to write this, and then I'm going to erase it, not carry it all the way through. Okay, distribute the 6 through. Now, this is all multiplied, so it doesn't matter what order I multiply them. And I could bring that 6 over in front of the ln, because it's commutative, right? And then I can get rid of it. I can rewrite it as an exponent. So instead of having this kind of complicated looking expression, I can simplify it just a little bit by saying 6, sorry, not 6, I'm going to raise that to power. Dy dx equals, not equals, I need more coffee. Oops, I guess I need more coffee. Ln x to the 6th. And then I'm going to do the same kind of thing over on the right-hand side, distribute the 5 through. So 5x over y dy dx. And then I'm going to write that as plus ln y to the 5th. Okay, so now I'm going to move everything with the dy dx to one side, all the other terms to the other. So, and can I make this jump? So what I'm going to do is I'm going to move this over here, move this over here. I'm going to bring that 5xy times dy dx. I'm going to factor out the dy dx, which leaves me this. So ln x to the 6th minus 5xy, okay, I hope you see that, equals ln y to the 5th minus the 6y over x. And then I'll divide both sides by that ln x to the 6 minus 5y to the x. So dy dx equals ln y to the 5th minus 6y over x over ln x to the 6th minus 5xy. I tried putting that in, it didn't like it. And here's the algebra they wanted you to do. They want to simplify this a little bit. And one of the tricks we can do, we might have learned this back with trig identities, we can multiply. Remember, we're going to multiply by a form of 1. Well, it would be really nice to get rid of that x, get rid of this x in the denominator, and it'd be really nice to get rid of this x in the denominator, or y in the denominator. So we could multiply both of these, this by x and this by y, and do some cleaning up. The trick that you can do is we're going to multiply by xy over xy. So now when I distribute this through, here, let me move this up. When I distribute that through, I'm going to get xy ln y. And now, to make it even easier, because the 5 is an exponent with something's being a log taken of, I can bring that 5 down in front now. And then here, the x, see how the x's cancel? So I'm left with 6y squared. No more fraction in the numerator. I can do the same thing in the denominator. Multiply it by xy, and I have an ln x, and I'm going to bring the 6 down in front. And on the next one, the y's cancel, so I'm left with 5x squared. And that's what they listed as the correct answer, and it's the most simplified, I guess. Okay, so that algebra was a little tough, I thought. Okay, so for this one, I actually messed it up. I messed up a chain rule, so I thought I should do this to you. And remember when I said you have a variable to a variable? That's a flag you want to use logarithmic differentiation. So we're going to break it up a little bit by taking the logarithm on both sides. Now let's do the derivative. So 1 over y dy dx equals, now 6 is a constant, so I can just bring that along for the ride. And then I see a product, x times that. So won't that be x over sine of 9x times the derivative of sine of 9x? This is the chain rule that I missed. Cosine of 9x times 9, right? Because it's another chain rule. Plus, the derivative of x is 1, so all I need is the ln of sine of 9x. And then we're going to try to clean this up a little bit. So 1 over y dy dx equals 54. Now, cosine of 9x over sine of 9x will be the cotangent of 9x. Plus the natural log of sine of 9x. And now we're going to multiply both sides by don't I have an x here? I missed an x here, guys. Sorry. You probably noticed that. See that x? I missed that. I had it included here. Then we're going to multiply both sides by y. So 54x cotangent of 9x plus the natural log of sine of 9x times that original y value. I'm going to have to squeeze it down here. Or maybe I can shrink it up a little bit here. I can. All right, so then I'm going to multiply that times sine of 9x to the 6x. And that is what they were looking for an answer. Okay, so watch out for those chain rules.